Hi everybody, I wanted to make a quick video to address some of your muddiest points from today's lecture. So the first question that I got was, how do I figure out when to use add versus addiu? I think a lot of people had this confusion. And the big distinction comes down to that add adds two variables or registers. So if you're not adding a constant or add immediate, you want to use add. So the syntax for add, again, is add the destination register and two source registers. And what this does is it adds the two source registers together and stores the value in the destination register. Conversely, addiu or add immediate adds a variable or register to a constant, like the number 27 or 12 or 1 or 7, whatever it needs to be. But it's always a constant, it's always the same value. So in this case, addiu takes a destination register, a source register, and a constant value. The constant always has to be the last value on the line. So addiu works by doing storing the result of S1 plus whatever the constant is, and the constant can be negative in the T0 register. That's where the destination is. Now, where some of the confusion comes from is that there's a variant called addi, which drops the u. The difference is that it's the same syntax, it does the same thing, but it throws an exception on overflow. We're not catching exceptions, so whenever we need to do an addi, add immediate, or add a constant, we use the addu just to be safe. Now, the next question was, why do we use BNE and BEQ backwards? And the reason why is because for BEQ and BNE, this means branch if equal, otherwise continue to the next instruction. And BNE means branch if not equal, again, otherwise continue to the next instruction. Now, when we say branch, we kind of mean skip to. And skip to means that we're going to skip something. So when we say something in C, like if I is equal to j, do this, we're actually saying if I is not equal to j, skip this, right? It's basically the same thing. It's a little confusing, but that's the way it works, and that's how we have to translate it into assembly. So here I've got the implementation, and here we've got the next part. Now, if we look at a naive implementation, if we were to use something like this, if we were to implement it like this, where we use BEQ at the top, and here I've got my registers all filled in. Let's look at how this executes, right? So here I've got BEQ, S0, S1. So I'm comparing S0 and S1, and then if they're equal, I'm going to skip to lab 1, which is what it looks like here. I want to do this part, right? So the two S0 and S1 are indeed equal, so we skip to lab 1. That brings our execution here. We add them together, execution continues, and we do subtraction. Everything looks good. Now, if we change S0 to 1 and execute it again, you'll see what happens. BEQ, S0, S1, and now the problem is that this says if they're not equal, go to the next one, which is exactly what we have to do anyway, right? So it does the addition here when we don't want it to. They're not equal, we shouldn't be doing this, right? And then it continues execution. So that's not cool. And you might think, oh, we can just swap sub and add, but the problem is that we have to skip one of these guys, and if we put sub here, we still have to do add, and we end up with the same result, right? Or if we don't, or if we put the add at the bottom and put the sub here, then we put the lab at the bottom, we end up not executing sub. It becomes a huge problem. So what we have to do is we use BNE instead. So we say skip the next instruction. We're basically saying skip the next instruction if this is true, and then go to the outside of the loop, right? So skip the body of the if statement if it's not equal, if it's the opposite. So here we've got if they're equal, BNE, they're not equal, if they're not equal, branch, otherwise if they are equal, go to the next instruction, which is the inside of the loop. And then we finish it off, everything's cool. Now, if we change the value again, be any. If they're not equal, skip to lab 1, which is the sub instruction. We skip directly there. Everything's kosher, and that's awesome, right? So I hope that clears it up. Next question. Can you go over the if-else statement? Absolutely. So the trick here is to write it from the bottom up, because basically we want to do whatever executes, whatever is more certain to execute first. So we'll start at the very bottom. We've got the I equals I plus 1. This is our next instruction. This is whatever comes outside of the if-else, right? So we put that in there straight up, right? It's a simple add I or add IU, S2, S2, 1, right? And the next part is the else statement. And we do this first because we know that if we get to the else statement, we want to go straight to the next instruction, right? We don't want to have to jump between them. So we do an else with our label, that's our subtraction, H and I and J, right? And then there's a kind of an implied statement in here. And basically what it's saying, above this else, there's something that says, if I executed this instruction, then I want to skip over the else and go straight to next, right? So we do, and the way we got there, we would have gotten there is if I is not equal to J. If we were executing this, then I is not equal to J. So we want to put a BNE there, or we can use a jump instruction like we talked about, right? So we can put our BNE there. If they're not equal, we want to go to the next instruction. That skips the else, and we go straight through. Next, we fill in the body of our if statement with an add, and then finally at the very top, we want to decide if we want to do the body of the if statement or the else, right? Because we already had the BNE, we need the BEQ, which is the other side. So if these two are equal, we want to skip this and go to the else statement, then do the next statement, which that does here. If they're equal, go to the else statement and go to the next statement. Now, it's important if the register you're comparing is modified in S2 and S3, you want to replace this instead of BNE with a J. That's the jump instruction. Now this always works, right? So instead of doing this might work as long as add is not modified, as long as S2 or S3 is not modified inside the if statement. But just to be sure, always use J. Use a jump instruction instead, because it's always going to be the opposite of this, and you don't want to have to think about whether or not it's modified inside of there, right? So that's a good one right there. That was a great question. Why use jumps in while loops? That's the next one. So this is a great question. This is awesome. This is very exciting. So here we've got our while statement and the corresponding loop. So what happens here is we're basically doing the same, doing a sort of opposite. We want to stop, or we want to skip the body of the loop if this is equal, right? So this is saying do the body of the loop while it's not equal. We can also think of it as skip the body of the loop if it is equal, otherwise continue doing it. And that's what we're doing here. So we say if they're equal, skip the body of the loop and just go to the next instruction. Otherwise, execute the body of the loop, which is this add, is the same thing, and then go back to the top. Now, we could implement this as a single branch if not equal statement, as like this, where I've got I do the body of the loop, then I check at the very bottom whether or not it's not equal, right? So I'm doing the body of the loop, then you can kind of think of it as kind of upside down. This is actually how we implement a do while loop rather than a just straight while loop, and the distinction is subtle, and we'll talk about that in a second. So here we've got the add, we add our two numbers together, I equals I plus j, then we do branch if not equal. So this is saying if I is not equal to k, we want to repeat the loop. So we go back up to the loop and we just keep doing this until it's not true. If it becomes, until it's not true. If it becomes true, it just goes to the next instruction, which is our exit. So we don't even need the exit label here anymore, but it still works. Now there's a caveat here. The warning is that this second implementation assumes that I is not equal to k on the first iteration, which may not be the case, which is not actually what we're saying in this statement. This says check this first, then do it, then repeat, right? Which is exactly what we do here. check this first, then do it, then repeat. If we were doing a do while loop using the same syntax, we'd have this implementation. So it's slightly different, a little bit of finesse, and things like that, but just watch for that. Finally, I got a request to do more interactive stuff. I totally can. We'll use MIPS a lot more in class on Thursday, and I'm very happy. I got some great questions, and this was excellent. So thank you guys, and I'll see you in class. Thanks.